Hello guys, welcome to the Java 0 to Infinity course. In this, we are in the series where we are going to master the Java the right way. This is going to be the third video of this series. In this video, we are going to master the JVM architecture. In this video, we will learn about the JVM architecture in great detail, and we will also understand the JVM architecture with real life example. So, without any further ado, let's start today's video. So, as we have learned in the previous video, how the Java code execute on the system. So we have learned that we write our Java code in .java file, that is human readable, and JavaC compiler compile this file into the .class file, that is known as bytecode, and then the JVM load this class and interpret this line by line and execute this bytecode. So in today's video, we are going to learn about the architecture of the JVM, like how does JVM execute this .class file in great detail. So let's start with this. Let's start. So before deep dive into the architecture of the JVM, first let's learn about what is the function of the JVM. So basically JVM does the following things. So JVM is responsible for loading the Java bytecode, that is this .class file that is created after compiling the .java file. The JVM takes this .class file and load it, then verifies this bytecode for the security, and then execute this bytecode. How does it execute? So first it converts this bytecode into the machine code, because computer can only understand zeros and one. So JVM will interpret this bytecode line by line, that is first convert it into the machine code and then execute it. Thus the JVM provides the platform independence. Thus we can say that the JVM is the execution engine of Java. So we have completed. So we have learned about the function of the JVM, like what is the function of the JVM. So let's now deep dive into the architecture of the JVM, like how JVM actually works. So basically there are 5 main components of the JVM. First one is the class loader, second one is the memory area, third one is the execution engine, and fourth one is the native method interface. It is also known as Java native interface, short form JNI, Java native interface. And the last one, fifth one, is the native method libraries. So these are the main 5 components of the JVM architecture. So this is the 5 main components of the JVM. First one is the class loader, second one is the memory area, third one is the execution engine, fourth one is the native method interface, or it is also known as Java native interface, JNI short form, and then the native method libraries. In today's video, we are going to look into each component in great detail. So let's first start with the class loader. So it basically performs the 3 functions. First one is the loading, second one is the linking, and third one is the initialization. So its main responsibilities is of loading, linking, and third one is the initialization. So let's study each one in detail. So what is loading? So basically loading means class loader loads the .class file into the memory, because the .java file that we have created is compiled using the JavaC compiler into the .class file. So the first phase is the class loader subsystem load this .class file from the disk. Where does this .class file is stored? In our computer. So this .class file is stored in our disk. So it is the responsibility of the class loader subsystem, class loader, that it loads the .class file from the disk into the memory. And it is not that like in our program, if there are like 6 classes and all that 6 classes will be loaded in the memory at once. No, the classes are loaded on demand. Like if there is a demand of some class, then only that class is loaded. So this approach is known as lazy loading. That is, suppose we have 3 classes like student class, and until and unless this class is not called, this class is not going to be loaded into the memory until and unless it is called. So the classes are loaded on demand, and that is called lazy loading. Now let's learn about the types of classes in Java. So what are the types of classes in Java? So basically there are 3 types of classes in Java. First one is the core Java classes, second one is the extension or short form for SC classes, and third one is the application classes. So there are three types of classes in Java, and in order to load all these three classes, there are three types of class loader. So there are three types of class loader for loading each types of classes. So Bootstrap class loader is responsible for loading the core Java classes. Extension class loader is responsible for loading the extension classes, and application class loader is responsible for loading the application classes. So as you can see, there are three types of class loader. First one is the Bootstrap class loader, second one is the extension class loader, and third one is the application class loader. Since there are three types of classes in Java, so for loading each types of classes, there are different types of class loader. Classes of Java. So what is the core Java classes? Core Java classes is the built-in classes of Java. It provides the fundamental features required to run any program, because so basically core Java, as from the name signifies it is the core Java classes. These are the fundamental features required to run any program. So all these features are provided by the core Java classes. Without the core Java classes, any program cannot be run. So basically core Java classes is required for every program. For example, for the input and output, core Java classes are required. For example, system.out.println hello. So if you are not familiar with this, so this is basically used to print anything on the console. We will learn about in detail. So this system class is the core Java classes, because it provides the core fundamental features to required to execute any program. Since input and output is a fundamental feature, it is required for running any program. So it is part of the core Java classes. Printing, and it is used to print the output to the console. Second, data types and the object. For example, string name Shubham. So here the string class is the part of the core Java classes. So basic handling text using the string class. So these are some of the example of the core Java classes. For example, java.lang.string, it is used for the text handling. It is a part of the core Java classes. Java.lang.system, it is used to handle the input and output. It is the part of the core Java classes. Java.util.arraylist, it is used to create the dynamic array. We will learn all about it. If you are not understanding, just remember it. Like, it is all the different types of classes available in Java. So first one is the core Java classes that provide the core fundamental feature to run any Java programs. So these core Java classes are always available, and there is no need to import it. So core Java, we can say that the core Java classes is basically the building block of every Java program. Without this core Java classes, any program cannot be run. So this core Java class is loaded by the Bootstrap class loader. So this core Java class is loaded by the Bootstrap class loader. So it is loaded by the Bootstrap class loader core Java classes. So let's study about what is the Bootstrap class loader. So I have already told you that Bootstrap class loader is responsible for loading the core Java classes, and the class loader, there is a hierarchy in the class loader subsystem. There is some hierarchy. So Bootstrap class loader is in the top of the hierarchy, and there is no parent of it. So its parent is none. So there is no parent of the Bootstrap class loader. And what is its responsibility? Its responsibility is to load the core Java classes from this path. So it is responsible for loading the core Java classes. And where does these classes are stored in our system? So these classes are basically stored in the disk in this path, Java home/library path. And this class loader, this Bootstrap class loader is not written in the Java. It is written in a native language like C++ or C, and it is not written in Java. So Bootstrap class loader is basically written in native language like C or C++, and it is not written in Java. And at hierarchy level, it is the top of the delegation chain, and there is not any class loader above of it. It is the root. So this is all about the Bootstrap class loader. Bootstrap class loader is in top in the delegation chain. It is responsible for loading the core Java classes. What is the core Java classes? The core Java classes provide the fundamental feature to run any program. So now let's move to the next type of Java classes. That is the extension Java classes. So extension Java classes, as from the name signifies, extension means there is some extension of extension. So let's study. So basically extension Java classes extend the Java functionality, like it provides some extra functionality. These are the classes that provide some extra functionality to the program. So basically extension Java classes are the classes that extend the Java functionality. It provides the advanced and specialized feature beyond basics. So what is the extension Java? Extension Java classes are the classes that extend the Java functionality and provide the advanced and specialized feature beyond basics. Its example is like data. For example, for the database connectivity, we use driver manager dot get connection. So this class, that is driver manager, is a type of the extension class, and it provides extra functionality to the user. Therefore, it is a part of the extension classes. And what does it do? It basically connects the Java with the database. And second one is the like example security. For the security and encryption, it is not the basic feature, it is the specialized feature. And for the specialized feature, there are some extension Java classes known as for the security and encryption. This is the cipher class, which is a type of extension Java classes which is used to encrypt and the decryption. And some of more example of the extension Java classes are like javax.sql, javax.crypto. It is used for encryption, it is used for the database. So it is all the type of the extension Java classes, and it is not always available. We need to import it. So what we can say that extension classes is the power up feature for Java. Like it provides some advanced and specialized feature in order to provide special functionality to our Java program. And this is loaded by the extension class loader. Since extension classes are loaded by the extension class loader, and extension class loader is also known as the platform class loader. Now let's learn about the extension class loader. So extension class loader is also known as the platform class loader. Its parent is the Bootstrap class loader. It is also known as platform class loader, and its parent is the Bootstrap class loader. And what is mean by the parent? We will learn it when we learn the delegation algorithm in the next slide. Then we will understand the significance of the parents of the class loader. So what is its responsibility? Its responsibility is to load the extension classes. And in the previous slide, we have learned about the extension classes is nothing. It provides some advanced and specialized feature for our Java program. So we can get its name, and this extension class loader is basically written in Java. And we can get its name by simply .class.get class loader return the name of the class loader that loaded this any class. So let's see it in example with. So let's see it with the help of example. For example, let's see the class loader of this class javax.sql.rowset is one type of extension classes, and let's see who is its class loader. .class.get class loader, and let's print it. So from here we can see that the platform class loader is responsible for loading this java.sql.rowset class, and this class is the extension class, and it is loaded by the platform class loader. Now let's see what we will get when we try to print the Bootstrap class loader. So as we know that the system class is a core Java classes, and it is loaded by the Bootstrap class loader. And let's try to print it, and let's see what we will getting. So from here we can see that it is written that the class loader is null. Why it is so? Because the Bootstrap class loader is written in the native language, that is C or C++. That's why we are not getting any class loader for it, but it is of the type Bootstrap class loader. But when we the extension classes, it is this rowset.class is extension class, and it is loaded by the platform class loader, which is also known as the extension class loader. So that's the whole about the extension class loader. And now let's learn finally about what is the application class. So application class is nothing, it is the class that is written by the programmer. For example, for us, when we write any classes, so then this my app is the type of the application class, and it is loaded by the application class loader. So what is the who is the parent of the application class loader? So the parent of the application class loader is the extension class loader. So parent of the application class loader is the parent of the application class loader is the extension class loader. And what is its responsibility? It load our application classes written by the programmer, or like us, any classes that we write it is loaded by the application class loader, and it is also written in the Java. So we can get the name of this application class loader by simply writing our class name and then .get class loader. It return the name of the class loader that loaded this particular class. So let's see with the help of example in this. So let's copy this line and let's print it, and here write the application class is loaded by this class load this. And what is the name of our class? The name of our class is main. So let's write main dot class dot get class loader. So let's see. So application class is loaded by, as from here we can say the application class loader. So as from here we can see that it is loaded by the application class loader. So here the system is of the type core Java core class, and it is loaded by the Bootstrap class loader. The extension is the type of this class is the type of the extension Java class, and it is loaded by the extension class loader. And this, the main class that we have written, it is a type of the application class, and it is loaded by the application class loader. And when we run it, we will get it. But why we are getting the null for the Bootstrap class loader? Because the Bootstrap class loader is written in the native languages, that is C or C++. That's why we are getting null here. So the extension class, the extension class is loaded by the platform class loader. It is also known as the extension class loader. And our main class, that is the application class, it is loaded by the application class loader. So there are three types of classes in our Java program. So, and for these classes, there are three types of class loader available in our application. So now let's learn about the delegation algorithm, like how these three class loader interact with each other, and the different class loader loads the different types of classes. So suppose in our program we are using any class, let's say the system class. So this system class is of the type core Java class, and it will be loaded by the Bootstrap class loader, as we learned from in the previous slide. So let's see how does this occur. So this is possible with the help of the delegation algorithm. So whenever a class is requested, for example in our program here we are using the system class. So whenever a class is requested, so application class loader gets the request. For example, whenever in our program we are writing any class, the request to load any class, so first this request is passed to the application class loader, that is application class loader gets this request. Now the application class loader will delegate this request to its parent, that is the extension class loader. So it asks the extension class loader to load this system class. So the system class does not directly look the extension class loader will not directly look the system class. It delegates this request to its parent, that is the Bootstrap class loader. Extension class loader delegates its request to the Bootstrap class loader. Now, so what happened first? So first the application class loader gets this request, application class loader pass this request to its parent, extension class loader pass this request to its parent, that is the Bootstrap class loader. Now the Bootstrap class loader get the request to load the system class. So now it will search that whether this system class is present in the core, whether this system class is present in the core Java classes. If it found this class, then the class is loaded by the Bootstrap class loader. Suppose so this way the core Java class is loaded by the Bootstrap class loader. Suppose there is one class that, suppose now we want to load some extension class. For example, in the previous example, rowset class. So again the request is first passed to the application class loader, application class loader will delegate this request to the extension class loader. The extension class loader will pass this request to its parent, that is Bootstrap class loader. Now the Bootstrap class loader will find whether this class is present in its core, whether this class is the core class or not. Since the extension class loader is not present in the core Java classes, so it failed. So it does not find. So now it passed this request to the extension class loader to load this extension class. Now the extension class loader will see whether this class is the extension class or not. So if it is extension class, then this class is loaded by the extension class loader. So this way the extension class loader is loaded by the extension class is loaded by the extension class loader. Now suppose there is some class, let's say the class that we have written, that is main, and this JVM request the class loader to load this main class. So first the application class loader will get this request to load this main class. So it does not directly load the main class. First it passes this request to its parent, that is extension class loader, to load the main class. Then the extension class loader will pass this request to the Bootstrap class loader. Now Bootstrap class loader will see whether this main class is the type of the core Java classes and present in the core Java classes or not. Since the main Java class is not the part of the core Java classes, so it will fail, and then it will pass this to the extension class loader. Extension class loader will see whether the main class is present in the extension classes or not. Since it is not the extension class, so it failed, and it will pass this request to the application class loader, and now the application class loader will load this main class. So this is the delegation algorithm, and this is the way the three class loader interact with each other. So if found, loaded it; if not found, child loads. For example string str hello. So application class loader will ask the extension class loader ask the Bootstrap class loader. Since the string is of the type of the string is the core Java class, and the Bootstrap class loader will find this class and directly load it. Bootstrap loads the class. So it's ensure that the core class is always loaded by the Bootstrap class loader. Since the request of loading any class is first passed to the Bootstrap class loader, and if the Bootstrap class loader is failed to load this class, only then this request is passed to the extension class loader. So second, for example, here is our user written class, that is my app. So the application class loader will first ask the extension class loader to load the my app, and then the extension class loader will ask the Bootstrap class loader. Now the request is this to the top, that is to the Bootstrap class loader. Since my app is not present in the core Java classes, therefore it Bootstrap not found, and therefore it passed this request to the extension class loader. Extension class loader also not found this class, and this request is passed to the application class loader, and then finally the application class loader will load this my app. So this is the way the class is loaded in this is the way the three class loader interact with each other in order to load the different classes. So what is the result of it? So our class is loaded by the application class loader. Now let's learn why there is need of delegation algorithm, and what is the need and what is the advantages of this delegation algorithm. So basically it provides the security, avoid the duplicate classes, and ensure that the core classes are trusted and original core classes are loaded. For example, suppose hacker create one string class, and this is the fake class of this string class is present in the core Java classes, and some hacker creates its own string class and try to replace this string class that is present in the core Java classes. So will JVM load this string class? So the answer is no. Why? So the answer is no, the JVM will not load this string class. Why? So suppose in our program we have used like string class. So the application class loader will get this request to load the string class. So application class loader will pass this request first to the extension class loader, and if the extension pass this request to the extension class loader, now the extension class loader pass this request to the Bootstrap class loader. Now the Bootstrap class loader there is no parent of it, so it will search whether the string class is present in the core Java classes or not. Since the string class is present in the core Java classes, so the class is loaded by the Bootstrap class loader. And which class? That core Java classes. So the class that the hacker has created was not loaded, because if any the request for loading any class is first passed to the top of the delegation tree, first to the Bootstrap class loader. If the Bootstrap class loader failed, then only the extension class loader get the opportunity to load the class. If the extension class loader failed to load the class, then only the application class loader get the opportunity to load the class. So if the hacker created any duplicate string class, then this string class will not be loaded. Instead of this, the original core string classes will be loaded. So in this way, the delegation algorithm provide the security and ensure that the core classes are trusted and cannot be replaced. So the Bootstrap already load the original string class, and delegation prevent the override. So what is the result? Ensure that the trusted classes are loaded. So in the summary, we can say that in the class loader subsystem, there are three types of class loader: Bootstrap class loader, platform class loader, it is also known as extension class loader, and finally the application class loader. The Bootstrap class loader could load the core Java classes, and if, for example, java.lang.string, java.util.start, and its parent is none. And the platform class loader load the extension classes, for example, java.crypto, java.sql, and its parent is the Bootstrap class loader. And the application class loader load the user defined classes, for example, the classes that we define in our application, and its parent is the platform or extension class loader. So this is all about the class loader. So in the class loader subsystem, there is a first part, loading phase, and we have learned in detail how does the different class loader work and how does the class is loaded into the memory. So now let's learn about second phase, that is the linking phase of the class loader subsystem. So what is the linking? Linking is the phase where JVM prepare the loaded class for the execution. So what is the linking? So linking is the phase where JVM prepare the loaded class for the execution. So there are basically three main steps in the linking phase. First one is the verification, second one is the preparation, and third one is the resolution. So basically in class loader subsystem, after loading, there is second phase known as linking. In the linking phase, the JVM prepare the loaded class for the execution, and in the linking phase there are three steps. First one is the verification, second one is the preparation, and third one is the resolution. So now let's start with the verification phase. So what happened? As from the name, you can guess that what is the verification phase. So in the verification phase, JVM check whether the bytecode is valid and safe. So in the verification phase, the JVM check the security of the bytecode, whether the bytecode is valid or not, and whether it is safe or not. So what it check? So first it check the format of the .class file, and it also ensure that there is no illegal memory access and there is no security violation. So all this checks is done in the verification phase. So if invalid, JVM throws error. For example, if we write int a is equals to hello, so basically a is of type integer, but we are trying to assign a string to it, so it is the wrong type, so it is invalid bytecode. So JVM will reject such code and throw us the error. So what is the result of this fetch? So it ensures that only the valid code runs in our computer. Now let's learn about the second phase, that is the preparation phase. So what happened in the preparation phase? So after the verification, after the bytecode is verified and ensure that the bytecode is safe and ready to run, then the second phase will come, that is the preparation phase. So basically JVM in this preparation phase, what will happen? So JVM will allocate the memory for the static variables. So now what is the static variable? So static variable is basically the variable for which we don't need to create the object, since Java is fully object oriented programming. So So everything in it in the form of class and the object. So static variable are those variables for which we don't need to create the object. We can directly access those variables using the class without the creation of the object. So these are the type of the static variables. No worries if you're not understanding it. Just remember that the static variables are the variable for which we don't need to create the object, and it can directly be accessed using the class. So what happened in the preparation phase? In the preparation phase, the JVM will allocate the memory for the static variables, and the variables are default initialized. That in this the original value of the variable is not assigned. In this the default value is assigned. For example, for the integer data type, the default value is 0. For the object type, the default value is null. Default value is null. So if you are not familiar with the data types, you can watch the data types in Java video of mine in the Codersphile channel. So in the preparation phase, the values are default initialized. For integer, the default value is 0. For object, the default value is null. For example, consider there is one class, and in this there is a static variable known as int x is equals to 10. So first this class will be converted into .ClassFile, and in the first phase this class will be loaded by the application class loader in the loading phase. Then in the linking phase, the verification of this class will be done, and this is correct. Then in the preparation phase, the memory is allocated for the x variable, and in this currently its value is 10, but in this phase the original value will not be assigned. In this the default value will be assigned. So for the integer, the default value is 0. So the default value 0 will be assigned in this static variable. So x is equals to 0, the default value is assigned in the preparation phase. So what does mean by the preparation? So preparation means the memory allocation for the static variables. And what is the static variable? Static variable are the variables for which we don't need to create the object, and we can directly access these variables using the class name. Let's see with the help of one example. Suppose let's create another class like demo class, and here let's define a static variable like int x is equals to 10. And here let's print that as, and what is our name? Demo dot x, and if we print it, it will be printed. Suppose first static. So we define the static variable in our new class static, and for the accessing this value we don't need to create the object. So we run it and the value gets printed. So basically here in the demo class, this variable x is the static variable, and for accessing this variable we don't need to create the object. As you can see from here, we directly access it using the class name. So in the preparation phase, the memory for the static variable is allocated, and it is default initialized. Suppose we don't write here static, and now if we try to access it, then it will give us the error. So in order to access it, now we need to create the object of the demo type. D is equals to new demo, and now we can access it with the help of the object, the non-static variable. And if we print it, now the 10 will be printed, because now it is not a static variable, it is an instance variable. So this is the difference between the instance and the static variable. So I hope you get. So what happened in the preparation phase? In the preparation phase, the JVM allocate the memory for the static variable, and the value are default initialized. Till now the original value 10 is not assigned in our variable. Currently the value is the default initialized, that is for integer it is 0. So what does mean by the preparation? Preparation is basically memory allocation for the static variable. Now let's learn about the next phase, that is resolution phase. So in the linking that last verification has done, preparation has done. In the preparation we have default initialize the value, and in last in the resolution phase, what happened in the resolution phase? So in the resolution phase, JVM convert the symbolic references into the actual references. What means by this? Suppose in our bytecode, this is the system.out.println. For example, it is our .java file, and it will be first compiled into .class file. So in .class file, it will be the system.out.println. So basically, it is the symbolic references. In order to execute the println method, the JVM needs its memory address, where this method is stored in the memory. Suppose here is the memory, and here there is somewhere the println method. So in order to execute this println method, the system needs the actual memory address, like where this println method is stored. So in the resolution phase, this whole line is replaced with the actual reference, like the actual memory address. So what is a symbolic reference? Symbolic reference means a name based reference stored in bytecode. So here the system.out.println is a symbolic reference, that is the function is referenced with the help of the symbol. So but it needs to be replaced with the actual name based reference. What is meant by the name based reference? That is actual memory address of the where does this method is stored. So in the resolution phase, this symbolic reference is replaced with the actual memory address. So the bytecode contains system.out.println. So the println method of the system class. So in this phase, this is replaced with the actual memory address where this method is stored. So this happened in the linking phase. So linking consists of the three phases: verification, preparation, and resolution. In the verification, we verify the bytecode. JVM verify the bytecode. In the preparation phase, it allocate the memory for the static variable and default initialize it. And in the resolution phase, the symbolic reference is replaced with the actual name based reference. Now let's see the third phase of the class loader subsystem, that is initialization phase. So first, what is the linking? Linking means the linking the name to the actual memory. So now let's learn about what happened in the initialization phase. So it is the phase where JVM assigned real value to the static variable. Till now in the preparation phase, what happened? In the preparation phase, the default value of the variable. So first, in the preparation phase, the memory is allocated for the static variable, but currently it is assigned its default value. Currently no real value is assigned to it. But in the initialization phase, actual real value is assigned to the static variable and also execute the static blocks. And the static, now we will learn, let's see what is meant by the static block and how. For example, here in example, suppose here is our demo class, and in this there is one static variable and one static block. So what is the static block? So these are the block that are executed once, per class. So what happened during initialization? So in the preparation phase, the memory is allocated for the variable x and its default value is assigned to it. Now during initialization, the x is equals to 10 is initialized. So in the memory, the 10 is assigned to the variable x, and also the static block runs. So this is the static block, and this initialization happen once per class. So once this class is loaded, so this initialization happen once per class. Let's see with the help of example. So let's see, here is our demo class, and suppose it is of type static variable, so that we don't need to create the object for it. And also let's create one static block, and let's print here the static block 1 is executed. And suppose create another static block, let's say the static block 2 is executed, and in the here let's, so suppose currently if we run it, suppose currently we run it, and we print here like demo.x. and now let's see. So as from here you can see the static block 1 is executed, static block 2 is executed. So what happened in the initialization phase, the static block runs and the x is equals to 10 is assigned to it, and the static block execute in defined order. For example, if the first static block is defined first and again the second block is defined below it, so first this block will be executed and then this block will be executed. So it means by the run in the defined order. For example, in the demo class, this static block is defined first and then it is defined, so that's why first this block is executed and second this block is executed. So this is meant by the static block. So what happened in the preparation phase? In the preparation phase, the value is assigned to the static variable and the static block is executed. So what is the use of the static block? So basically the static block is used to configure one-time configuration to the class. Like if you want to configure the class before loading it, then this static block is used, and this initialization happens once per class. For example, here if we define again, suppose here if we access the demo.x again, so the static block will not be executed 2 times. The static block will be executed only 1 time. So that's the meaning of the that initialization happen only once per class. And what is mean by the lazy loading that we have learned earlier? So let's remove it. So suppose if we don't use the demo class, then the demo class will not be loaded. For example, here as you can see that the demo class is not loaded, that's why its static block is not executed. So it is meant by the static lazy loading. What is meant by the lazy loading? The lazy loading means that the class is loaded on demand. Suppose here we are using the class, then the class will be loaded. And which class loader is responsible for loading it? .class.get. As you know that it will be loaded by the application class loader. As you from here you can see that it is loaded by the application class loader. So this is all about the class loader subsystem. In the class loader subsystem, there are 3 parts: loading, linking, and initialization. In the loading phase, the .class file is loaded into the memory. In the linking phase, what happened in the linking phase? In the linking phase, there are 3 steps. First, the bytecode is verified, then all the static variable all the memory is allocated for the static variable, and in the resolution phase, all the symbolic reference is replaced with the actual memory address. Then in the initialization phase, the actual value is assigned to the static variables and the static block are executed. So in this way, the class loader subsystem ends here. So now you will be thinking like, what is the difference between the preparation versus initialization phase? Like what happened in the preparation phase and what happened in the initialization phase? So in the preparation phase, the memory is allocated for the static variable and the value is default initialized. It is in the initialization phase that the actual value is assigned to the static variable, that is 10. So I hope you understand the class loader subsystem. So now the first component is complete, that is a class loader. Now the second component of the JVM is the JVM memory, and it is also known as JVM memory or runtime data area. JVM memory or runtime data area. So what is it? It is the memory structure where JVM stores the data while running a program. So what is the runtime data area? So runtime data area is basically a structure where JVM stores data while running the program. So now you will be wondering like, why the JVM need the memory in order to run the program? So basically JVM needs the memory to store the objects that are used in the program, execute the methods, keep the variables, track execution. Without it, the program cannot run. So what is the runtime data area or the JVM memory? So it is basically a memory structure where JVM stores the data while running the program. So while the program is running, it is the memory structure where the JVM stores the data while running the program. What does this JVM memory or the runtime data area store. It stores the object, it stores the methods, it stores the variable, and it also tracks the execution. Without the memory, the program cannot run. So in order for the better organization, JVM divide the memory into 5 parts. So first one is the method area, second one is the heap area, third one is the stack, fourth one is the PC register, also known as program register, program counter register, and fifth one is the native method stack. So this is the 5 part of the JVM memory. So first one is the method areas, heap area, stack area, PC register, and native method stack. JVM divide the memory into 5 parts. So let's first start with the method area. So what is the method area? So basically the method area, what is meant by the method area and what is meant by the shared. So as we know that Java is the multi-threading language. So there are basically different threads in the Java that can be run. So this method area is shared by all the threads. Currently, if you're not familiar with the thread, then no problem. Just remember that the thread is like a different independent workers that execute the program. So just remember that this method area is shared among all the threads. So this method, so what does this method area stores? So this method area stores the class metadata, or the static variable are stored in this method area only. So the static variable here is the method area, and what does it store? So it stores the class metadata like the class name, structure of the class, method code, and constructor. All these things are stored in the method area. So basically in the class there are different, all the class metadata, static variables, method code of a class, and constructor, all are stored in the method area. And when does this memory is created? So this memory is created at the JVM startup. So it is the method area. Method area store the class metadata, methods, static variables, and also store the constructor. And this method area is shared among all the threads. So if what is the thread? Thread is the independent unit of execution of the program. So if you are not aware of the threading, then no problem. Just remember that thread is nothing. It's a like an independent small unit that executed. Now then it is the method area. Now let's learn about what is the heap area. So what is the heap? So basically heap store all the object, that is instance of a class. So what is the object? Object is instance of a class. So heap is the area where does the object are stored. It is the heap. It is the heap that stored the object, and the garbage collector works in the heap only. What is the garbage collector? We will see in futures, in next slides. And from here the objects are never explicitly deallocated. It is done automatically by the garbage collector. For example, if once the object is created in the heap, then it is not explicitly deallocated. It is done with the help of the garbage collector. Come here and deallocate this object. And this heap is created at the JVM startup. This heap is created at the JVM startup. For example, if we write as student s is equals to new student, basically it is the method of creating the new object in the Java. So what happened? A new object is created in the heap memory, and this heap memory is also shared among all threads, and this heap memory is also shared among all the threads in the program. So this is the heap memory. What does the heap store? It stores all the object, and the garbage collector works here. Once deallocated, done automatically. Now the stack. And the third memory area is the stack. What does the stack do? So it is not shared. Each thread has its own stack. Each thread has its own stack. Now what does the stack stores? So stack stores the stack frames. And what is its stack frame? So what is the stack frame? So stack frame is nothing. Every time a method is called, JVM create a stack frame for it. So basically stack frame contain the important information. Stack frame is basically stores the local variables and the other important data about a method. So every time a method is called, JVM create a stack frame for it. What does the stack frame hold? The stack frame hold the local variables like method parameters and variable declared inside the method. For example, suppose there is one method like add int a comma int b end. So this is the method. So what happened in the stack frame? In the stack frame for the thread t1, so a method is called, so add stack frame will be pushed into the stack, and in the stack there is a local variable and the parameter. For example, here a is the local variable, here is the parameter. So this a and b will be stored in this stack frame, and this is unique per thread. It is not shared among the threads. So what does the stack frame store? Stack frame store the local variable and the frame data like info about which method to return after execution. So the stack, we understand about the stack. Stack is basically, it is not shared among the thread. Every thread gets its own stack, and stack store the stack frame that stores the local variable and the frame data like where to move after the function ends. And finally the program register, program counter register. So each thread has its own program counter register. It is like it stores the memory address of the current instruction. For example, the bytecode is loaded into the memory, and each instruction has some address. So the program counter stores the current executing instruction of the current thread. It stores the address of the current instruction. So what is needed for the program counter track the execution of the thread. Why? Now you will be asking one question like, why each thread needs its own program counter? So because each thread in Java run independently. Now it is a concept of the multi-threading. If you know it, then it's well. If you don't know, just remember that each thread in Java run independently, and each thread execute different part of the code. Suppose there are different thread in the system like T1 and T2. So each thread in Java runs independently, and each thread can run the different part of the code. Therefore JVM gives each thread its own program counter, so that JVM give each thread its own program counter, so that it's know which instruction currently the thread is executing. So each thread has its own program counter. Now next one is the fifth, is the native method stack. So what is it? So it stores the information related to the native methods. So what is the native methods? So it is the method written in the language other than Java, like C or C++, and C or C++. So what does this native method stack store? Native method stack is a stack for the native methods. What is the native method? So basically with the help of Java, we can also call the other method written in other language like C or C++, and it is done with the help of the native method interface or JNI. We will learn this concept in great detail in the upcoming slides. So just remember that native method stack is a stack for the native methods that store the information about the native methods. And what is the native methods? Native methods is a method that is written other than the Java like C or C++. Now these native methods is not executable by the JVM directly. They run inside the native OS using the native libraries, and the JNI provide the interface for it. We will learn it in the upcoming slides. Now it completes the JVM memory. So basically JVM memory is divided into the 5 part. So method area store the class level information, heap store all the object, and garbage collector work here. We don't explicitly deallocate the object from the heap. Garbage collector comes and remove the object from here. Then we have the stack. What is the role of the stack? this is not shared among the threads, and these two method area is shared among the threads. It is shared among the thread and it is not shared among the, each thread gets its own stack area, PC register, native method stack. Now heap store all the objects, stack store the stack frame, PC register store the address of the current executing instruction, and native method stack store the information about the native methods. Now let's learn about the third component of the JVM architecture, that is the execution engine. So what is the execution engine? So basically till now the class loader loads the class file into the memory, allocate the memory for the static variable, store all the information in the class, store the information in the method area, stack frame for each thread in the stack. Now there is need for start executing the program. So this execution, the part is done by the execution engine. So what does it do? It executes the dot class or bytecode. For example, the dot class file, there is some instruction like instruction, line by line instruction number 1, instruction number 2, instruction number 3. So what does the execution engine does? It reads the bytecode line by line. It first read this line, then read this line, then read this line. Uses the data present in the JVM memory and information present in the various memory area and execute the instruction. So what will do? First, it is in the bytecode. So first it will convert it into the native method, native language, that is 0s and 1. Now execute it with the help of the data present in the memory area. So now execution engine consists of the three parts. First one is the interpreter, second one is the JIT compiler, that is also known as just-in-time compiler, and third one is the garbage collector. So the execution engine consists of the three parts: interpreter, just-in-time compiler, and garbage collector. So let's study each in detail. So what does the interpreter, as we have already know that interpreter is nothing but it executes the bytecode line by line. For example, for each line, what it will do, for example, here is our dot class file, and in the dot class file there are different lines, like for example line number 1, line number 2, line number 3. So what does the interpreter will do? So interpreter, for each line, the interpreter take each line, convert, so it is currently in the bytecode format, convert it into the 0s and 1, that is native machine code, and now execute it. So convert the bytecode into native code and then execute it. So what is the feature? So it is very slow, but it is simpler. So suppose there are some part of the code, suppose there are some instruction. For example, here is our program, and suppose there is line number like 2, 3, 4, like suppose 2, 3, 4, and there are different types of lines, and these two lines, suppose what is the problem of this approach? Suppose there is 3 line in our code, like 2, 3, 4 line number, and it is repeated again and again in our program, like it is repeated here also, it is repeated here also, like this 2, 3, 4 instruction is used various time in our program. So again and again there is need to convert bytecode into the 0s and 1 and then execute it. So but it is very slow. So in order to solve this problem, just-in-time compiler come. So what it will do, it convert, for example, in the our code that is 2, 3, 4, it is used frequently. So what it will do, it will compile this frequently used part into the machine code, 0s and 1s, and wherever these lines come together, it directly convert this into the native machine code. So there is no need for the line by line interpreter. So that's why it is known as just-in-time compiler, JIT compiler. So what it will do, so it basically convert the bytecode into the native machine code, and it convert the frequently used code into the native machine code. So there is no need to interpret it again and again. So it ensures there is a faster execution in our program. So this is the advantage of just-in-time compiler. What does it do? It first identify the most frequently used part in the code, take it and compile it into the machine code, and then again there is no need to again and again interpret it, directly used it in our program. So it result in the faster execution. It is its advantages. Now the execution engine, the third component of the execution engine is the garbage collector. As from the name signifies, garbage means something trash and collector means collecting it. So what does the garbage collector do? So it removes the unused object from the heap. We have learned that in our heap, the object are stored in the heap. So what it will do? So it will remove the unused object. For example, there is one object in the heap that is not used in the program. So for example, in the line number 1 the object is used, but in the next line the object is not here. So it removes the unused object from the heap. As we learned earlier, the objects are created on the heap area. Eventually some object will no longer be needed. Garbage collection is an automated process that removes the unused object from the heap. For example, here we have created one object that is a student, but now we have defined s is equals to null. Now we can't access this object again. So reference removed, object unreachable. So this student that is created in the heap become unreachable. Therefore the garbage collector will come and remove this object from the heap. So this is the role of the garbage collector. So what does the garbage collector do? Garbage collector remove the unused object from the heap. Let's learn about the Java native interface. What is it? Java native interface. It is also known as native method interface. As from the name signifies, native method interface or Java native interface. So native means that the code that is written in the machine specific languages like C or C++. So what is JNI? So JNI is basically an interface between the Java side and the C side, that is native code. So JNI is basically a bridge that connects the C side and the Java side. So before learning the JNI, first read about some of the limitations of the Java, that because of which there is a need of the JNI. So let's read about it. So what Java cannot do? So Java cannot directly access the hardware access. Java does not have the direct hardware access because Java is run inside the Java virtual machine. Therefore the Java language therefore the program written in Java cannot directly access the hardware. For example, camera, sensors or USB, it cannot be directly accessed by the Java programs. But the code written in the native like C or C++ can directly control the hardware like camera, sensor and the USB. Second thing, like Java cannot call the OS specific system calls. On the other hand, the native code can interact with the OS APIs like Windows, Linux calls, etc. Java cannot interact with the device driver, but the code written in the C or C++ can directly interact with the device drivers. Java cannot do the low level memory manipulations, but native code can do it. Java cannot utilize the maximum performance for the heavy task, but since the code is written in the native language, it ensures the high speed execution, no JVM overhead. Java cannot use the existing C or C++ library directly, but in the native side it can directly use powerful native libraries like the OpenCV or GraphQL. So these are some of the limitations of the Java. So in order to solve all this limitation, the JNI was introduced. So in order to overcome all these limitations, so basically that's why JNI is needed to connect native side to the Java side, so that the full performance of the Java can be utilized. So the full performance of the native code can be enjoyed using the Java side. So what is JNI? So JNI stands for Java Native Interface. It is also known as Native Method Interface. So what is it? It is a bridge that allows Java to interact with the native side. So what is? So Java alone cannot access the hardware, perform OS level operation, achieve maximum performance. So JNI helps Java to call the native methods and use the system level features. So what happened? So when a Java calls a native method, so whenever a Java calls a native method, the JVM forward this call to the JNI, and the JNI call the, so whenever there is a code in our program that is the native code, the code written in the C or C++ is called in our Java program. So it forward this call, JVM forward this call to the JNI, and JNI Java native interface call the function of the C or C++ side. And now this code, this native code does not execute by the JVM. It is executed by the native OS using the native libraries, and the result of this operation is passed to the JNI, and JNI will then pass this result to the Java side. So result returns to the Java using the JNI. Let's see a working example of how the JNI help us to call the native method from the Java code. So here we have one code written in the Java language demo.java, and there is one method that is the square root method, and it is the type of the native method. So basically it is defined in our native code, that is C or C++, and here we are calling this method obj.square root, that is the native method. So you don't need to know how this code has been written. I am showing this example in order to only give you practical understanding, like yes, we can call the native method using the Java code. So basically this square root is the native code, and that is defined here in the demo.c. As you can see here, this is the square root function, and in this function we have written like hello from the native C side, and it uses the standard one of the library of the C language, that is math.h, in order to find the square root of the given integer a. So let's run this code, Java demo. So as you can see from here, we are getting hello from the native side, and the result is equals to 5. So what happened here? So when the JVM come to this line and start executing it, it see that obj.square root. So it see the square root function, and it see that it is of the type native method. So what it will do? So Java calls a native method. So upon seeing the native method, JVM forward this call to the JNI. For example, here we have our square root function which is of the type native, so it forward this call to the JNI. JNI forward this call to the C or C++, C in this our case C code, and in that the square root function is defined. Now this code is run in the native OS using the native libraries, like here the native library is the math.h that we have used in our program, and it run in the native OS, that is not in the JVM. It run in the native OS using the native libraries, and it get executed, and the result, that is here the square root of a, this result is passed to the JNI. This result 5 is passed to the JNI, and JNI forward this result back to the Java side. From here, as you can see, the square root is found and returned. Now the JNI returned this result into the result, and the result is printed here. So from here we can see that we can call the native code using the Java, and this is possible all due to because of the JNI Java native interface. So now this completed the fourth component of the JVM architecture, that is a native method interface. So now let's learn about what is the native method libraries. So native method libraries are the collection of the native libraries required for executing any methods. So they include the libraries written in the language C or C++. For example, in this our previous code example, first we have written our code in this native language, and then we converted this code into the native library, that is demo.dll, and we loaded this native library in our program in order to use this code. So this is the native libraries. Native libraries is basically a collection of native library required for executing any native methods, and they include the libraries written in the C or C++ language. So this completed our fifth part of the JVM architecture, that is the native method libraries. So this all completed the JVM architecture. So till now we have studied the whole JVM architecture in detail. Now let's see the working of this JVM architecture with the help of one example, so that we can get a clear understanding like how this JVM architecture help in the execution of any Java program. So for this example, we have one student class, and in the student class there are two attributes, ID and name are the two attributes of the student class, and there is one static variable school that will hold the school name of the school for the particular student. And then we have one static block that is executed once per class during the initialization phase, and in the static block we are assigning the variable to the static variable school. So the static block can be used to assign this value to the static variable. Then we have constructor, student constructor, for the declaration, for the creation of this object of the student class ID and name, and we are assigning the ID and name to the object. Then we have one display method that will display the ID and name of the student, ID, name and school name of the student. Then this is the main method. This is going to be the entry point of the program, in which we are creating the two instances of the student class, that is two object of the type student class, S1 name Ram and S2 name John. And then we are calling the method display on the student S1 and the S2. So it will display the name of the S1 and S2. And finally we are accessing the static variable school. Since school is the static variable, we don't need to create the object for accessing it, and we can directly access this variable directly using the class name. So this is the whole program, and I have also written it, and let's run it. What it will do, let's see. So basically it's printed the executing static block and assigned the static variable Codersphile school to the school static variable. Then the program execution begins from this main method. So two instances of the student is created, S1 and S2, and when we call S1 dot display, the RAM 101 RAM and Codersphile school get printed, and when we type S2 dot display, the ID, name and school for the second student John is printed. And finally we are printing the static variable school using the class name. So this is the whole program that is it doing. Let's see now in detail like how JVM architecture help in the execution of this program. So as we all know that the first phase of the execution of any Java program is like we have our .class file, and the first step is to load the class file into the memory. So for the loading of the ClassLoader subsystem is responsible for loading the class to the memory. And the ClassLoader system, there are three phases. First one is the loading, second one is the linking, and third one is the initialization. So in the loading phase, as we have already done, so in this case, this request for the loading of student class is first passed to the application ClassLoader. So as we all know that the student application ClassLoader first forward this request to its parent, that is extension ClassLoader, and the extension ClassLoader will also pass this request to its parent, that is Bootstrap ClassLoader. Now the Bootstrap ClassLoader will see whether the student class is present in the core Java classes or not. Since the student class is the application class, we have created it, that's why it does not present in the core Java classes. That's why the Bootstrap ClassLoader will now pass this request for the loading of the student class to the extension ClassLoader. Since the student is also not the extension Java classes, so it will not find the class, and it will forward this request to the application ClassLoader. Now the application ClassLoader will load this student class into the memory. So the ClassLoader subsystem will find the student class and load the student class from the memory, from the disk to the memory. So it read the bytecode and bring this to the JVM memory and storing all the class metadata into the method area. So what it will do? So now the application ClassLoader will load the student class into the method area, and what it will store now in the method area, the student and its constructor, like all the metadata of the student class, like its constructor student will get stored in the method area, and the method displays also get stored in this method area. and main method is also get stored in the method area. So this is the first phase in which the class loader subsystem loads the class into the memory. Now let's move to the second phase, what happened in the linking phase. So in the linking phase there are three sub-steps. First one is the verification, second one is the preparation, third one is the resolution. First let's see in the verification phase. So in the verification phase, the JVM will verify the bytecode and ensure that this bytecode is safe to run. Now the second phase of the linking is the preparation phase. What happened in the preparation phase? So in the preparation phase, the JVM will allocate the memory for the static variable. In this case, school is the static variable. So it will assign. It will allocate the memory for the static variable school, and currently it will not store the actual value of the school. Currently it will hold the default value, since school is of type string and the default value of the string is null. So the default value will be assigned to this school, that is null. So in the preparation phase, only the allocation of the memory is happen. The initialization will happen in the initialization phase. And now, so the second phase is completed. In the second phase, what happened in the preparation phase? The memory is allocated for the static variables, and in the static, and the default value is assigned to the static variables. So for the string data type, the default value is null, so the null is assigned to the school static variable. Now there comes the third phase, resolution phase. What happened in the resolution phase? So as we have already done in the resolution phase, all the symbolic references is replaced by the actual reference. The actual reference means the actual memory address of the display method is replaced. So in the symbolic reference, what will happen? This will be replaced by the actual address of the display method. It will be replaced by the actual address in the resolution phase. So this completes our linking phase, and now the final comes the initialization phase. So what happened in the initialization phase? So in the initialization phase, the JVM will execute the static block. So in the initialization phase, this static block will be executed and assign the actual value to the static variable. So we have our actual value is assigned to the static variable school. Since this block will get executed, as value is assigned to the static variable. If it is not written here, if it is written here also, then still the initialization will happen in this phase only. That is, the actual value of the static variable will be assigned in the initialization phase only. In the preparation phase, only the allocation of the memory will happen and the default value will be assigned to the static variable. The actual initialization will happen in the initialization phase. So the role of the class loader will end here. Now the class loader has loaded the class into the memory, allocate the memory for the static variable, and initialize the static variable. Now after doing so, the role of the class loader is end. Now the execution engine will take the control of the program and start executing the instruction. The class loader prepare the class for the execution. Now it is the responsibility of the execution engine to start executing the program. So now the execution engine will start executing the program. So what happened? So after initialization, so in the class loader system, after initialization, the JVM, which part of JVM? Execution engine will create the main thread to start executing the program. Since in Java, everything is executed by the thread. So by default, the execution engine create the one main thread to start executing the program, and this main thread start its execution from the public static void main method. So after initialization, JVM create the main thread to start executing the program. Now as we have already learned that now the main thread is created, and as we have already learned that each thread has its own private stack. So the main thread stack is created in the JVM memory area, and also each thread has its own program counter register. So this is the program counter register for the main thread. So this is the program counter register for the main thread. So till now the main thread stack is created and the program counter register for the main thread is created, and currently it will store the address of the current executing instruction. Suppose the address of the current this is the address of this instructions. So currently it will store the address of the current executing instruction. Suppose the main thread start its execution from here, so that's why it will store the address 0 in it. So now what will happen? So first the execution of the program will start from the main method. So as we all know that what does the stack store? So the stack stored the stack frame, and what is this? For each method one stack frame is pushed into the stack. Since it is the main method, so for the main method the main frame is pushed into the stack. And we have already learned that what does the frame contain? So frame contain the local variables, argument, and the local variable and the arguments. So what are the local variables and argument in? So this argument, this is the argument in this main method. So this main frame will store this argument. And what are the local variables in this main method? So s1 and s2 are the two local variables. What are the local variables? So the local variable is some variable that are declared inside some method. So this variable s1 and s2 are defined inside the main method. That's why the s1 and s2 is the local variable that belongs to the main method. So the main frame will contain the local variables and the arguments. So argument and s1 or s2 are stored in the main frame. Now, so I have already explained that the main method is the entry point of the program. The main thread starts the execution of the program from the main method. Now a new stack frame is created for the main method. New stack frame, that is the main frame, is created for the main method and pushed to the main thread stack, and this main frame is pushed into the thread stack. Now this thread holds the space for its local variable, which are s1 and s2, and the argument, that is args. At this point these local variables are just references pointing to nothing yet. Now at this point these local variables are just a reference variable and it is currently pointing to nothing, that is it is pointing to null value. Currently it is null. Now till now the execution the main thread start its execution from this method, and currently for the execution of the main method it prepare it. So what does it do? It will first push the main frame into the stack. And what does the main frame contain? The main frame will contain the argument and all the local variables into it. Now till now the local variable is pointing to nothing, and that is it is currently pointing to null. All the thing is ready for the execution of the main method. So now the execution engine will start its execution from the line number 0. So what it will do? So first it will convert it into the as we all know it is a bytecode, and it will be converted into native machine code, and then it will be executed. So what will happen? So JVM will execute this line, new student 101 ra. So as soon as the execution engine see the new keyword and then the student, what it will do? So the JVM will allocate the memory for the student object, since student is an object, since as we are creating the instance of the class, and the instance of the class using the new keyword, and the instance of the class is the object. So the JVM will allocate the memory for the student object in the heap, and what will be stored in this object? In this object will store the instance variable and name inside the object. For example, this is our heap memory area, and in the heap memory area the one object will be created for this line, new student, and there is some address to it, and currently it is not containing anything. Currently it's holding its default value. For integer it is 0, and for the string it is null. So it is currently its default value. So as soon as the execution engine see the new keyword and then the followed by the student keyword, it create the object for the student class in the heap, and currently it is not containing any value for the instance variable. And what are the instance variable that will be stored? So these are the instance variable id and name. This is the instance variable that is, it is created per object of the class. So id and name is in this object. And now this line will be executed like new student 101 and ram. So this is basically a constructor, and from where does this constructor is loaded? So this constructor code can be found in our method area. So since this is a method, and for the execution of the method, its frame must be pushed into the stack. So in the stack, the student frame will be pushed into the stack. So the constructor will be called from the method area, and its main frame, student frame, will be pushed into the stack. And what does this student frame will contain? As we have known that the stack frame contain the argument and the local variable. So in the constructor of this student, what is the argument? So id and name is the argument, and is there is any local variable? No, in here there is no local variable. So this student variable will only contain id and name. And what it will contain? It will contain the value that is passed into it, that is 101, and in the name it will contain the ram. Now the program counter register will shift to this line number, that let's say it is line number, it is execution number like 12 or something else. Let's say its address is 12. So now this program counter register will hold the address for the current executing instruction. So this is the current executing instruction. And what does this mean? This dot id is equals to id. What it will mean? This here, this keyword signifies that the object in the heap. So this means the object in the heap, and id means that its instance variable will be assigned to id, that is this instance variable will be assigned to this id, that is id. Now the id will be assigned to 101, and now after executing it, the next line will be executed. Program counter will be registered, program counter will be updated to point the next instruction, that is this dot id. So now it will be printed this dot name is equals to name. So what does this mean? This means the current object, and name is like its attribute that is currently null. So this dot name is equal to this name. So the name will be assigned to ram. Here the name will be assigned to ram. Now the method will, this method is finished. This constructor method is finished. So this stack frame will be popped from the stack, and now this execution is complete. Now after executing, it will return the address of this object that is created in the heap, and it will get stored in this s1 variable. So what will happen? So this student frame get popped from the stack, and what happened? It will return the address of this newly created object, and it will get stored in the local variable s1. So the local variable s1 will only contain the reference to the object that is created in the heap. So the s1 will only contain the reference to the object that is created in the heap. Now the similar thing will happen for the s2. First this line will be get executed. This line will be executed. The memory is allocated for memory is first created for the for this, and then again this method is get executing, and the stack frame is pushed into it, and its name is assigned, and similarly the id and name John is assigned to this object, and its reference is stored in the local variable s2. So this is the way, like statement number 1 and statement number 2 will get executed, and its two objects are created in the heap, that is s1 and s2. S1 will point to this object, that is 101 and ram, and s2 will point to this variable, that is 102 and John, and the address is here. And while the other end, in the heap area, only the object is stored and the object instance variable of the object is stored. All the methods of the class is stored in the method area, and it is not replicated per object, it is per class. Only the instance variable is created per object. As you can see from here, there is only id and name that is created for every object. On the other hand, all the method like display method and student and its constructor is stored only once in the method area. So these two lines get executed. Now the third line s1 dot, now the program counter will now point to this, and the execution engine will start executing this line, that is s1 dot display. Let's see how it will run. So now, till now, in our method area will contain the student constructor method and static variable school, and in the main thread stack, it will contain the argument s1, and this s1 will pointing to the object that is created in the heap. Now the program counter register will point to the next instruction, that is s1 dot display, and the execution engine start executing this instruction s1 dot display. Let's see how this instruction will get executed. Now the JVM uses the references, as we have seen that in the resolution phase, this s1 dot display is replaced with the actual address of the display. So JVM will use this reference in the s1 to find the object in the heap, since s1 contain the address. So first what it will do, it will first find the object that is present in the heap. Now the object is found here, object is found in the heap. Now what it will do, now it will look at the object class information in the method area to find the display method bytecode. Now it's seen that there is one display method, so it will find the student class and its student class in the method area and find the display method. So it found, now the execution engine found the display method, and now it find its bytecode of this display method. And what is the bytecode of this display method? This display method contain this system.out.println id, name and school. Now it will find it. Now since display is a method, so a new stack frame is pushed into the stack, that is display stack frame is pushed into the stack. And what does the method is doing? Method is printing the id, name and school. Since id is the instance variable, so the object will print the id from here, the name from here, and since school is the static variable, it take the school variable from here and it will print the value, that is 101 RAM, and the static variable it take from the Codersphile. This is the way the s1.display method will be executed. So first what it will do, first the execution engine will use the s1 to find the object in the heap, and then it will see the display. So first it will find the bytecode of the display in the method area. Since all the method and the class metadata is stored in the method area, it found the bytecode for the display method, and now the display frame is pushed into the main thread stack, because for the execution of any method, its stack frame must be pushed into the stack. And since it does not, this display method has not any argument and does not have any local variable, so it will store nothing. Now it will directly print the id, name and school. Since id and name is the instance variable, so it will take, this display method will take this value from the object, that is 101 and RAM, and the value of the static variable will be taken from the method area, since it is a static variable. So this is the way the method s1.display will be executed, and it will print the 101 RAM and Codersphile. Similarly, the s2.display method will be executed, and it will print 102 John and Codersphile. Now once the execution of the system.out.println finished, the display frame will be popped from the stack. and the main thread will leave, and the program counter register will update it to point to the next instruction, that is s2.display. Now similarly the s2.display method will execute and print the 102 John and Codersphile. Now the program counter will update and now point to the this last line, that is system.out.println student.class. Now let's see how does this method system.out.println student.school will printed. Since a school is the static variable, so static variable can be directly accessed using this class, so it will use the school. So first it will find the school class in the method area and dot school. So dot school means the variable present in the method area of the student. So it will directly print the Codersphile school in the console. And now the main method, so that is the way this program is executed, that is 101 Codersphile school, and this is the way the program is executed. Once the main method is finished, its stack frame is popped and it will destroy all the local variables. So once the main method is end, its main frame is popped from the stack, it will be destroyed, and all the local variable will be destroyed. All this will be destroyed. Method end, but once the method is end, but the method ending does not destroy all these objects that are present in the heap. So these are the objects that are present in the heap. So now the main method has finished executing. So its stack frame is popped from the stack, destroying all the local variable of the main method, but the method ending does not destroy the object present in the heap. So still the object in the heap remains alive. So now there are no variable that is pointing to these objects present in the heap. Now the garbage, so now no local variable is pointing to the object, therefore garbage collector will hit it. Now garbage collector will come and see that there are no local variable that is pointing to these objects. Since there are no local variable that is pointing to these objects, this object cannot be used, and therefore these are garbage. So the garbage collector will destroy all these objects. Garbage collector will come here and destroy all these objects that are present in the heap. Now the main thread, that we have was having now has no work to do, and this main thread will terminate and our program has finished executing and the JVM will shut down. So this was whole flow how any program is executed using the JVM architecture, and I have already explained you how the JNI help in executing the native C or C++ code from the Java side. So I have not added the JNI part in this example to make it simple. So this was all whole the way how the JVM architecture works in Java. I hope you enjoyed the video, and now there is a crystal clear concept of the JVM architecture, different component of the JVM architecture, and how all these components interact with each other in order for the successful execution of any Java program. So that's all for the today's video. Thank you.